This is the explanation of my final project for Parallel Algorithms 5260, Computer Science at the University of Tennessee, Chattanooga. Our project was to create a parallel program that was relevant to our domain. Since I come from a healthcare background, I chose to implement a parallel program to identify high-risk cardiac patients. My background is primarily in the emergency department, and in 2021 there were approximately 6.5 million emergency department visits in the US just related to chest pain. Not all of these chest pain patients have coronary artery disease. They may be from muscle strain, anxiety, or acid reflux. So in order to determine which patients are high risk for coronary artery disease, there is a well-validated tool called the heart score that is frequently used to risk stratify patients. The heart score has 5 different criteria, and each criteria, depending on the answer, assigns a point value. And then this is summed up to get a total value, which is used to risk stratify the patients. Low-risk patients have a 1.6% chance of experiencing any type of adverse cardiac event, such as a heart attack or death. A medium risk patient has a 13% chance of experiencing those events, and a high risk patient has a 50% chance. So it's a great way to either discharge patients that are low risk and have a low heart score, or to provide additional validation to justify admitting those patients for further coronary workups. Because of the amount of chest pain patients that come through the emergency department, I thought it would be helpful if hospitals and analysts had a way to look at all the patients that came in with chest pain and then determine what percentage of those were actually high-risk patients that needed further admission or workup, or to evaluate if they actually did have adverse effects if they were discharged home. There's lots of different data that could be pulled from the patients that have heart risk scores documented in an electronic health record. So for this study, what I did is I generated a pseudo EHR for each patient. Generally, electronic health records would have thousands and thousands of data points in the record, not just the heart score. So I wanted this program to feel a little bit more valid and that there would be more data that it would have to sift through in order to get to the heart score before it would total the heart score and then save all of our high-risk patients. So in my very basic electronic health record, I added a patient identification, systolic and diastolic blood pressure, heart rate, oxygen levels, lab values, and then all of the 5 criteria associated with the heart score. And then I created 2 versions of the code because I wanted to compare whether a parallel program would actually be more efficient and save time compared to a sequential code. So the first code I wrote was a sequential code. So it literally just goes through each patient. It generates random values for the data that I just explained. And then within that for loop, it would analyze each patient to determine whether they were high risk, medium risk, or low risk. And I chose just to separate the high risk patients out and save all of their associated data into a CSV file. To make it similar to what the amount of volume would be, I chose 1 million patients. So each time the code ran, it would iterate through 1 million patients, generate the data, analyze the data, and then save the high-risk patients. So that was the sequential version of the code. The second code I wrote was using MPI, which is the message passage interface. And I chose this because I felt like it would be a good option to parallelize the code and send it to separate processes. Since we had access to the high-performing computers at UTC, I could increase the number of processors compared to just using like a general desktop. So initially the MPI environment was set using the functions MPI init MPI com rank, and MPI com size. This is basically just to set up the MPI environment, get the functions started, and then appropriate the right size and how many processes we would need. Each process would have a separate rank identification number. So that would be used to divide the workload into specific processes. And then those processes will then pull the information and put it back into the root. The size is needed to specify the memory that was going to be needed. And this is just used as a pointer. The command line, when the program is run, can specify how many processes need to be used. And I will go over how many processes we did a little later. I used a non-blocking technique, MPI gather, because there wasn't any type of race conditions that I was worried about with this code, since they were all being generated separately and then gathered back at the end to the root process. So initially, MPI gather was used to gather all the generated data that each process generated for its specific number of patients. So the million patients were separated into separate processes. Each process was responsible for generating the data, analyzing the data, and saving the high-risk patient data information. After this, after it was all gathered, the MPI reduced it into our high-risk patients that we needed. And then from there, MPI gather V was used to essentially take all of the high-risk patients from the processes and gather them back into the root process. And the difference between MPI gather and MPI gather V is that MPI gather V allows for different data sizes, because we would expect a different number of high-risk patients from each process to be coming in. So it's a little bit more dynamic and flexible that way. From there, it was all gathered back into the root. It was initially all processed as a vector and then flattened into an array. And then this data was saved into a CSV file as well. I used timing MPI W-time on this program to calculate the time of execution. And I used just a standard timer on the sequential version to calculate that as well. So the results, the sequential code, I ran 3 different ways. I ran it standard, and then I ran it optimized to a level 2 and optimized to a level 3. The first program without any optimizations completed in 0.90 seconds. The second program was executed and completed in 0.63 seconds. And the third program did not show that much improvement with the third level of optimization, and it was 0.62 seconds, pretty much the same as the second level of optimization. When the MPI code ran, this is where we specified the number of processes, and I ran it 4 separate times with 2 processes, 4 processes, 8, and then 32. And this is where we really saw an improvement in time. As you can see in this diagram right here, this is where it ran with 2 processes, and the initial time was 0.49 seconds, which was almost half of what the initial sequential version ran. And then as we went to 4 and 8 and then 32, we were able to drop that time down to 0.13 seconds. To actually evaluate efficiency, we did speed up calculations between the different programs. And let's see, the speed up achieved on the sequential version, when looking at the non-optimized versus the optimized level 3, the speed up was 1.4. And then in the MPI version, when looking at 2 processors to 32 processors, we achieved a speed up of 3.8. So looking at the fastest sequential version to the fastest parallel version, our total speed up was 4.8, which is very significant when you're looking at large amounts of data to process. The limitation on using MPI is that you do need a computer with a large number of cores. You're not going to see as much of a speed up if you're using this on a regular desktop that might just have 2 to 4 cores. But if you can use a computer that has more than 8 cores, or at least 8 cores, then you will see the speed up that can be achieved using the parallel algorithm. So that is the conclusion of my project. We were able to demonstrate that a parallel algorithm can be used to extract and generate and extract data for patients with high-risk heart scores. And then this data can be used and further dissected to help improve patient outcomes. Thank you.